Okay, so on our topic in roots, we're going to look at a subtopic of rationalizing the denominator. And this might sound quite complex, but actually it just uses things that we've seen already. So to get you into the topic, I just wanted to do a quick recap on rational numbers, which we looked at last year. What are rational numbers and how do we define them? So if you remember from last year, we had 4 sets of numbers that we defined. We had n, z, q, and r. And if you remember, now the natural numbers were our counting numbers. So starting from 0, they included 1, 2, 3, and carried on infinitely. Z were our integers, and that included all of the negative whole numbers as well. So that included -3, -2, -1, as well as 0, 1, 2, 3, etc., etc. So Z was much, much bigger than n, even though n was infinitely large. We have infinitely more negative integers. And that was an interesting point. I wonder if you remember at the end of one of the videos last year. Then we moved away from our whole numbers into Q, and these were the key ones that I wanted to refer to today, our rational numbers. And these were all the numbers that could be written in the form of a fraction. So they can be written as a fraction, which means that their decimal representation terminates or repeats infinitely, so is a recurring decimal. And then we had our real numbers are all the numbers that you can think about. And this one also included some irrational numbers. So we had certain numbers that were rational, certain numbers that were irrational. So we had 0.5 was rational, because that can be written as a fraction and a half. However, we met some that were irrational, such as the square root of 2, which was not an element of the rational numbers. And if you remember, also pi was not an element of the rational numbers, for example. So anything that can be written as a fraction is rational, anything that can't is irrational, and this generally involves roots, and particularly roots of prime numbers are not rational numbers. So, therefore, in these examples, the fractions have an irrational denominator. And I'll give you 3 examples. So we have A, 1 over root 3. B, 1 over the square root of 3a minus 2. And C, A minus B over root A plus root B. And you'll note here that the square root signs are separate, so this one's contained under one square root, and these two elements are separate. And you'll remember from class that this is absolutely not equal to this. We can multiply them and join them together, but we can't add them and join them together. Okay, so we have 3 things here that have an irrational denominator, and depending on the calculation, having roots in the denominator can be annoying. So we need to get rid of the roots in the denominator. and make it rational. And this is where this phrase, rationalizing the denominator, comes from. So we are going to rationalize the denominator. Okay, so the key step in this procedure is to expand the fraction sensibly. So, let's just have a little recap on what this word expand means. So, to expand a fraction, if I had a fraction a half, let's say, let's expand a half. This means I multiply the numerator and the denominator by the same thing, which is exactly the same as multiplying by 1. So, fraction doesn't change because it's the same as multiplying by 1. And I'll show you in a concrete example with a half how this would work. So if I multiplied a half by a fraction that had the same on the top as on the bottom, so I could choose 2 over 2, 3 over 3, 4 over 4, anything over anything. I could even choose x over x if I wanted to, as long as x wasn't 0, of course, because we can't divide by 0. And you see how you could cancel the two x's here and have 1 over 1, which is the same as 1. So this would give me x over 2x, which is exactly the same as a half. They're equal. So in this case, we don't have an equation, but we can multiply the top and the bottom by the same thing and be safe in the knowledge that we don't change the fraction itself, as long as we don't have 0 on the denominator, otherwise that changes things. So, it's like multiplying by 1. And this is a very rare case in which you can multiply something that's not an equation, and because you still end up with the same thing. So, we need to expand the fractions sensibly. Now, sensibly is the second important part of this. And for our first two examples above, this is going to be really easy. For the third one, it's not going to be so easy. So, for the examples above, we had, for our first one, 1 over the square root of 3. Now, our aim here is to get rid of the root in the denominator. The goal is to make this a rational number. So therefore, we need to choose a fraction that has the same numerator and denominator that would turn this into a rational number. So the sensible choice here is, of course, again, the square root of 3. So multiplying across the top, I have 1 times the square root of 3, which gives me the square root of 3. And then if I multiply these two together on the bottom, I could do this as 3 to the power of a half times 3 to the power of a half, which is, of course, then, using the addition rule that we had for multiplication, 3 to the power of 1, which is 3 itself. Or you can just know that the square root of something times by the square root of the same thing is the thing itself. So here, root 3 was a sensible choice, because now we have a rational denominator. Although you may argue that this looks like a more complicated fraction, that sometimes it can still be useful even for simple examples like this. When we have fractions involving algebra, like b, this trick becomes even more useful. So we have b, we have 1 over the square root of 3a minus 2. And then I'm going to do exactly the same. I'm going to multiply by the root of 3a minus 2 on the bottom and the root of 3a minus 2 on the top, which gives me the root of 3a minus 2 over, then this times this is just the thing itself. So 3a minus 2. And again, I have a rational denominator here. C, however, is a little bit trickier. Let me delete these two, so I have space for C. So, in C, we had a minus b over the square root of a plus the square root of b. Now, if I were to do the same thing here, if I were to multiply top and bottom by exactly what's in the denominator here, then let's have a look at what we would get in the denominator of our solution and see if it's rational. We won't worry about the top, because we're first of all worried that our denominator is rational. So this is the same as doing the square root of a plus the square root of b times by itself. And we're going to have something up here that we're not worried about yet. So we have our something up here. Then the square root of a times the square root of a will give us a itself. So far so good. However, the square root of a times the square root of b gives us the square root of a times the square root of b. It doesn't change. It can't get any smaller than that. And again here we have the square root of b times the square root of a, plus at the end it becomes nice and rational again. The square root of b times the square root of b is b itself. So on the denominator here, I've ended up with a, there's something on the top, a plus 2 times the square root of a square root of b, plus b. This is not what we want. So here, multiplying by exactly the same thing doesn't work. If you have more than one separate square root in the denominator and they're not multiplied, then just multiplying the same thing is not going to work. So let's go back and try something different. Please note this calculation down, just so that you have a record of why this doesn't work and how this doesn't work and why you need to choose something different. So, because my intention here is to rationalize the denominator, I'm going to use my knowledge of multiplying out brackets of binomials to give us something that definitely is rational on the denominator. So I'm going to choose the square root of a minus the square root of b this time. And again, we have to have the same thing on the top so that it's like we're multiplying by 1, otherwise the whole thing doesn't work. And because I know this is going to work now, I'm going to multiply out the top. So I'll just write it in brackets first. Okay, now on the bottom, I've got this times by this. So root a times root a gives me a. Root a times negative root b gives me minus root a root b. Here we have root b times root a, so plus root b times root a. And then root b times negative root b gives me minus b. And you see these two cancel each other out, because I have minus ab, or minus root a root b, plus root a root b, because multiplication is commutative, that works. So I have a minus b times root a minus root b over a minus b. And because this is a whole term and this is a whole term, these two can also be cancelled, and my denominator actually now is just 1. So I definitely have a rational denominator. And my solution to this, I'll write it over here, but you can write it a little lower in your book, is just root a minus root b. And we're done. Okay. I'd like to practice this in the next video. I'm going to give you a couple of exercises to try, and then if you're unsure about how to proceed with them, then come and check in the video, and you can also check your solutions. So they will be 92, 93, and 94. I'm going to do part D of each of those exercises. So between the two videos, try them and see how you get on.